Last time we learned about complex numbers. Now we will discuss about power series. Uh, Let us first discuss what is power series. It is an infinite series of the form summation of a sub n times x minus c raised to n, evaluated from n is equal to 0 to infinity. And this expression can be also expressed in this form: a sub 0 plus a sub 1 times x minus c, and so on. This will be the expansion form of our general form of the power series. Okay, so now our goal for the power series is to learn how it is worked and its application on our course. And one of these applications are the Euler's identity. We will briefly define or derive what is Euler's identity. Now, if we assume that this function has derivatives of every order and we can find them all, we will be arriving in the series Taylor series. A Taylor series is the representation of a function as an infinite sum of terms that are calculated from the values of the function's derivative at a single point. Remember, at a single point only, and if we are going to center this at 0, we will have the Maclaurin series. Maclaurin series is a type of Taylor series. This is the Maclaurin series, and we are going to use this in deriving the Euler's identity. So we all know that if we evaluate e raised to x, just disregard the I here first. If we are going to evaluate e raised to x at 0, we will have this expression 1 over n factorial times x raised to n. Now, if we are going to add the imaginary part here, this is the Euler's identity, and if we are going to expand it, we will have 1 plus ix plus 1 half ix squared plus 1 6 ix raised to 3 or cube. And if we are going to notice, and we are going to separate the real parts and the imaginary parts, that will result to this expression. And we can notice that this expression is equal to the cosine x, which is equivalent to this 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial, and so on. And if we are going to proceed on the imaginary part, we will have this expression, and this expression represents the sine x. Sine x is equal to x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial, and so on. And if we are going to sum up all of this, we will have our Euler's identity, which is equal to this. This is our Euler's identity. That's how the Euler's identity is derived. Okay, now we are now prepared to solve differential equations with the use of power series. Now we will assume that y is equal to etc., which is equal to now we should always remember that if we are using the power series in getting the solution of a differential equation, I think we should have memorized the derivative of y, and it's also the second derivative because it involves second derivation of our equation. Then the double second derivative is equals to now in order for us to compare the expressions for y and y double prime, we rewrite y double prime like this. Okay, now we are now going to substitute this expression and this in our original differential equation. So we have okay, so since we have the same n and we also have the same x raised to n, we can now factor out x raised to n. Please note that cn plus 2 and cn plus 2 plus cn are just subscripts. Don't get confused. Now, if two powers are equal, then the corresponding coefficients must be equal. Therefore, the coefficients of x raised to n must be 0. And if we are going to get cn plus 2, we have